Okay, so welcome to Lecture 4 of Introduction to Quantum Computation for the summer 2020 term at Uni Paderborn. Today the topic is going to be no cloning, entanglement, and density matrices. I hope you guys had a good weekend. Before we begin, some quick announcements. So assignment 4 will be out soon, meaning over the next days. And last Friday we tried for the first time for the tutorials Big Blue Button as a venue, I guess, and that seemed to work well enough. I think we can continue to keep using it moving forward. Okay, so again, you need to look up your Panda account for the code, the access code for that. Just as a heads up, in general, we are not recording the tutorials. There are a few reasons for this. The main one is that, the tutorial is meant to be a time for private discussion in some sense among the students and the instructor, so that, and that's not something I want to publicly broadcast out, of course. And at the same time, of course, to put anything on YouTube, I would need your permissions and things like this. So, let's not go there. Okay. Okay. So that's all I want to say in terms of announcements. Today we've, the last weeks we've basically covered the basic postulates we need to start talking about quantum mechanics. Okay. And without loss of generality, that is in some sense everything you need to know. But, of course, there's always more to learn, and that is also true for quantum mechanics, right? And so today what we're going to do is we're going to take a direction which is in the sense of, rather than jumping into, say, algorithms right away and thinking about things in that direction, what I like to first do is take some time to really just play with quantum states, get comfortable with the Dirac notation, and in particular to learn density operator formalism, okay? And because I feel okay, in my personal kind of opinion, when one is learning quantum computing, I prefer to have a better grasp of, the underlying mathematics first before jumping into things like algorithms. And that's just the approach I like to take, okay? So basically, before you play with your toys, I like to get to know the toys first, right? Okay, so the quote atop today's lecture is a very famous one by Erwin Schrödinger, who's, of course, very famous for his Schrödinger's cat experiment, which we already talked about. The other thing he's very famous for is Schrödinger's equation, right? Which is basically an equation which describes how quantum systems change in time, basically. Okay. By the way, we will not cover that equation in this course because it's not a physics course, right? And I mean, the equation is implicitly already baked into postulate, I guess, 2, which was on quantum gates. Okay. The unitary operations, they come from Schrödinger's equation. Okay. Anyway. So this quote says, entanglement, which is one of the topics for today's lecture, is not just one of many traits, but the characteristic trait of quantum physics. Okay? And so as we'll see today, one of the, quantum mechanics has many strange phenomena that have no classical counterpart, and entanglement is certainly one of those phenomena. And, this troubled many great physicists at the time, and, we'll talk a little bit more about the history when we get to it. But for today, the idea is that, I want to introduce the notion of entanglement because it'll help us start to understand the difference between, classical states, which are things like strings, and things that are genuinely quantum, which are these entangled states. And once we start doing that, then we're going to have to start thinking about this density operator formalism, which is going to allow us to say, well, if I have a state which is entangled across many parties, how do I describe just one subsystem of that entangled state? And for that, we really do need the density operator formalism. Okay, so that's how everything kind of ties together for today's lecture. The one thing that sort of doesn't fit, but which you cannot have a quantum course without talking about, especially when you're talking about, trying to understand quantum states, is the no cloning theorem. Okay, so I want to start with that. It is a super simple theorem that is super important, right? So let me start with that. Okay, this doesn't necessarily have, of course it has to do with entanglement, but, a priori, just a statement of it. Well, no, actually, I suppose it doesn't have anything to do with entanglement. The statement and the proof don't require entanglement to be true, right? It really has to do with non-orthogonality of quantum states and the linearity of quantum mechanics, that everything has to be linear in quantum mechanics. Okay, so what is the no cloning theorem? So this is section 1 in the notes. So the idea is as follows. So again, there are many things we take for granted, right, in classical mechanics that just aren't true in quantum mechanics, right? So one of the things we saw, for example, was well, okay, let me not go there. The example here that we want to cover is copying things, right? So if you have your assignment, let's say you type it up in LaTeX, right? You could always create a classical copy of that, right? Of that bit string that describes your LaTeX file. But quantumly, the analogous task right here, which we'll call cloning or copying, basically, if I give you a quantum state, let's say, and you don't know what the quantum state is, right? It turns out to be impossible to copy that state perfectly. Okay, and that is the no cloning theorem. Okay, and we can actually prove this. Okay, so we're going to prove it, but the first thing, of course, we need to formally formalize the statement. What does it mean to be able to clone something or not to clone something, right? And then we can prove the statement. Okay, so and in general, that's again one of these life lessons, right? That when you're working in a technical field, especially something like abstract math, like in quantum computing, you really, before you prove anything, the first thing you want to do is you want to formalize it, right? You want to write down exactly the spaces you're working in, what is exactly the statement you want to show or you think you want to show, and then you go ahead and you try and show it. Okay, and a lot of times that, a lot of the difficulty is just in that formalization process. Okay, so what does it mean to say first that we can or cannot clone? Okay. So the claim is the following, right? So let's claim, or let's make an assumption, and we're gonna, maybe I'll write it this way, assumption. So let me formalize the notion of cloning like this, okay? And we're gonna prove that this assumption cannot hold. We're gonna give a contradiction, right? So the assumption is that there exists a unitary U, okay? And I'm just going to do this over qubits, but of course you could extend this. So this is a linear operator that acts on 2 qubits. Okay, so it takes 2 qubits to 2 qubits, which for any input psi, okay, so just, it's a single qubit state. Okay, so for any single qubit state psi you give me, what it will do, it will maps, so let me be clear. So U acts on 2 qubits, 1 and 2, right? So it will map psi on the first qubit, and I have a second register here, right? And this is supposed to equal to 2 copies of psi. Psi 1 tensor, sorry, maybe I shouldn't, for consistency I should put the index outside to clarify that we're acting on that qubit. Okay, so over here what we're saying is that, sorry, this is not pretty, I'm not happy. Okay, good, that's a bit better. Okay, so what we're saying here is that, if I take 1 copy of psi, right, and I have 2 registers here, and I apply the unitary, it should create a second copy of psi in a second register, right? And these should be in tensor product, they should be uncorrelated. Okay, and I've left this space blank here, and you might ask, what should I put here? Right? What initial state should we have in that register? And it turns out it doesn't really matter. You can pick your favorite initial state. As a simple exercise, you can, once we do the proof, you can try and convince yourself that the proof goes through for regardless of what initial state I choose here. So I'm just going to choose ket 0. Okay? And usually that's what we'll do, right? Ancilla qubits will typically, workspace qubits will typically just be initialized to 0. Okay, so how do we get a contradiction, right? I mean, we're going to do a proof. So the claim is the following. The claim is that this assumption, this one, is impossible. Okay, so how do I prove it? Think back to your standard proof techniques, right? Proof by construction, proof by contradiction, proof by induction, for example. Here we're claiming that something is not possible, so typically you want to use something like contradiction, right? So here's my proof by contradiction. So always remember to state your proof technique in the beginning. Makes for good proof writing. So let's assume that the claim is true, and then we'll see that we arrive at a statement which is nonsense, right? Which is just not possible. Okay, so what do I know? Suppose I have 2 arbitrary states. Okay, so consider that I want to clone. So 2 arbitrary states, psi 1 This is psi1, psi2. Okay, and they're both single qubit states. I don't necessarily know what they are, and I want to clone these, right? So what do I know? So by the assumption, and maybe I should give this thing a name, right? Let's call this assumption 1. So assumption 1. So by assumption 1, right, I know two things, right? I know that if I take U12 and I apply it to psi on 1, tensor 0 on 2, I end up getting psi, tensor psi on both qubits, right? And likewise, this is a cloning circuit, or a cloning unitary, and it's supposed to work for any input you give me. Sorry, let's be consistent with my notation. It's supposed to work for any input you give me. So this is psi 1 on 0. Okay, and then so here I get psi 1 in both of these. I don't like this notation. I'm going to quickly change this. So this is psi, and this is phi. Okay, so then I don't have to worry about drawing these indices here. So this is psi, and this is just going to be phi. Okay, I'm just going to quickly redo this. No, too much. Okay, psi and phi. Good. Okay, so here I want to say psi tensor 0, right? This goes to psi tensor psi. And this is phi tensor 0. And this goes to phi tensor phi. Okay? So this is the assumption. And now what I know is that now I can do two things, right? I have a pair of equations, and I have a left side and a right side, right? So what I can do is I could take first the inner product of these two guys. So let's do that. So let's take the inner product of these two and see what we get, okay? I mean, a priori, it's not entirely clear why you'd want to do this. So let's see, right? So if I take the inner product of these two guys, what I'm going to get is, this top term over here, right, that I'm going to take the bra of that. So I'm going to get psi tensor 0, right? And then I'll have U12 dagger. Okay, so that's the bra of the top term. Okay, and now I'm going to take the second term, the bottom term, and this is phi tensor 0, right? Okay, so let's just work this out. What is this really? Well, this is just psi, and just so you see, I'll do it kind of explicitly. So U12 dagger, U12, right? Phi tensor 0. Okay, and of course U12 is unitary here in the middle, so this term is going to disappear. It's just going to go to identity. Okay, so I'm going to end up getting psi 0, and just so you start getting used to this, I'm going to start dropping these tensor products, right? And just leaving them implicit, like we said we do in the previous lecture. Okay, and remember, of course, this is on qubit 1, qubit 2, and the tensor product basically does the following. It whatever's on qubit 1 gets sandwiched together, and whatever's on qubit 2 gets sandwiched together. Okay, and this term is just 1. Right, okay, so we don't really care about that term. Ket 0 is a unit vector. Okay, so the point is that the inner product of this left side is just going to be the inner product of psi and phi. Okay, that's all I know. But now, of course, the left side is equal to the right side, so if I take the inner product of these two now on the right, in principle, I should get the exact same answer, right? So let's see what we get. So if I do psi tensor psi on the left, and on the right we do phi tensor phi. Okay, and remember this is qubit 1, 2, 1, 2. Then again, the properties of the tensor product tell me I'm going to get 1. I'm going to get psi phi, psi phi. Okay, so what is this really? This is just going to be psi phi all squared. Okay. So here are my two answers, right? I have, when I took the inner product of the right-hand side with itself, I got the inner product of psi and phi squared. But when I took the inner product of the left-hand side, I got just the inner product of psi phi to power 1, right? A linear term, not a quadratic term. Okay, so if I call this equation star and this one star star, then together, if I combine these two equations, what I see, of course, is that this implies that these things are supposed to be equal, right? Right, because we started from the left and the right side were supposed to be equal, right? And so what is this though, right? I mean, the inner product of these two vectors is just a complex number, right? I mean, let's just call it C. It doesn't really matter what name I choose. And what I'm saying, therefore, is that, C equals to C squared for this complex number, whatever that is, right? And there are only two complex numbers that satisfy this property, right? That they equal to their square. And they are, think about it for a second. What can we conclude, right? There are only two numbers, right? 0 and 1. That's it. Okay, so what this tells us basically is that the only way, star and star star can simultaneously hold, which is supposed to happen, right, is if the inner product between the two vectors I wanted to clone is either 0 or 1. Okay? Okay, so now that means that the input has to be restricted, right? So what does this mean? This means that either psi and phi they have inner product 0, which means that they're orthogonal, or they have inner product 1, which basically means that they're the same vector, right, up to a unit phase. Okay, but there's a keyword in my assumption that contradicts this, right? So the proof rules out not all cases of inputs, right? But for most cases of inputs, it rules them out, right? And I claimed here in the input that there exists a fixed unitary U. Here's this, right? So this comes first, such that for all inputs, okay, so here I'm using a for all quantifier, right? For all inputs, such and such holds. Okay, so, and this proof clearly shows that this is false, right? The only inputs for which this could potentially hope to work is if you have an inner product of 0 or 1. Okay, so this means that, so this implies a contradiction. Whenever you do this, we have a contradiction. So U cannot work if psi and phi, they satisfy, the inner product is between, let's say, 0 and 1, right? Okay, so if the absolute value of the inner product is between 0 and 1, this can't work. Okay, so, and that's the proof of the claim. Okay, so we have a contradiction, so the assumption is false. It is not true that there exists a single unitary U, a cloning circuit, so that for any quantum state you give me, it produces a perfect copy of it. Okay? And so you might wonder, what's the deal with this, right? Why does this case kind of escape your attention, right? Why does the proof kind of break down when the input states are orthogonal or the same? And, intuitively, okay, I won't prove it here. This is actually there's an exercise here right at the bottom of the section 1. You can actually clone if you know the basis you're working in. Right, okay, and all you want to clone are the basis vectors for that basis, right? Then you actually can clone, right? And this is crucial, right? Because that's the case in which you're cloning classical data, right? This allows you to clone basically ket 0, ket 1, right? So if you know you're working in ket 0 and ket 1, and I give you a ket 0 or ket 1 to copy, and you don't even know which one it is a priori, then of course there has to be a unitary that does that copying for you. Otherwise you couldn't copy classically either, right? So that's what this key exception is allowing you to do. So this allows copying, for example, the pair ket 0, ket 1, right? If all I'm giving you are these two states, you should be able to create copies of them without knowing which one you're about to get, right? There should be a fixed circuit that does this. Okay, so try the exercise at the bottom of the, in the course notes at the bottom of section 1 to see if you can solve that, right? So that's trying to give you there you have to give a quantum circuit that will clone the states 0 and 1, for example. Okay, so that's all I want to say. The point of this initial part of the lecture is that this no cloning theorem, right? That there is no fixed unitary that for any input you give me, it will create a perfect copy of it. Okay, and this is a genuinely quantum phenomenon. Okay, so with that said, we can move on to kind of the more central focus, right? I mean, so the point of this lecture is I'm trying to motivate the density operator formalism, and the natural way to do that is to start by talking about entanglement. Okay, and entanglement is fun, right? It's one of those really weird things about quantum mechanics, and so that in itself is worth discussing, frankly. And I'll try and give you some sense as to why. Okay, so quantum entanglement. Sorry, this is a section, so I might want to just write it that way. Okay. Okay, so in the last lecture, what we saw is that we can use entanglement as a resource, right, to do a task. And the task we did was teleportation, right? So remember that last lecture, we used the entangled state, the so-called Bell pair, phi plus. And remember this was, let me just briefly refresh your memory. This is just 0, 0 plus 1, 1, right? We'd use this to do teleportation. Okay. Okay, so, but of course I haven't really told you, I gave you a formal definition for what entanglement is, but, you know, we haven't really had any sort of philosophical discussion about what this is supposed to mean and what is it good for in some sense, other than, of course, teleportation, right? So let me just very briefly tell you about the history of entanglement. I mean, so kind of the field's view on this has really changed over the years, right? So quantum mechanics is about 100 years old now, maybe, you know, give or take a bit longer than that now. And, you know, the term entanglement, it actually comes from Schrödinger himself, okay? It was coined in 1935, and at the time it was called Verschränkung, which is the German word. In colloquial non-physicist English, Verschränkung means basically like the folding of the arms like this, okay? And of course it's supposed to, well, okay, my understanding is it's supposed to impart this idea that you have two particles which are really kind of tied together, if you will, right? For native German speakers, feel free to correct me if I'm mistaken. Okay, and you know, entanglement has been the subject of very extreme debate. Okay, so there's this famous paper by Einstein, Podolsky, and Rosen in 1935, which is nowadays called this, you know, EPR paper, right? 1935, right? And what this paper argued was that, you know, there has to be something missing in quantum mechanics. It can't be complete, right? The description of reality that quantum mechanics prescribes must be missing something. And essentially the argument boils down to the fact that quantum mechanics predicts that states like this Bell pair should exist in nature. Okay, and then, you know, Einstein and Podolsky and Rosen did not like this, right? And so, so this was, you know, quantum mechanics must be incomplete. That was the argument that they put forth. Must be incomplete. Okay. And along comes John Bell, and this is where the word Bell pair comes from. You know, it's named after him, right? John Bell in 1964 comes along, and he offers this idea of these non-local or Bell what are now called Bell inequalities, right? So they're basically tests that you could run in a lab. Okay, so they're named in his honor. They're tests that you can, in principle, run in a lab, right? To test whether nature really behaves in this non-local fashion, right? That whether does entanglement really exist? Okay, so these are mathematical equations you can write down, and if entanglement exists, then you'll be able to violate kind of the measurement statistics that are supposed to be that classical measurements. Okay, this is an inequality that is based on the measurement statistics, expectations on measurement statistics, right? And the inequality says that any classical system must satisfy this inequality. And only if you have quantum systems can you violate this inequality, okay? And that's what Bell inequalities are. And nowadays, you know, we, in the CS community, we think about them in terms of something called non-local games, which is a way to a less mathematical way. Of course, it's still highly mathematical, but it's not abstract math in some sense. It's now phrased in terms of an interactive game between parties, right? And we'll talk about these next lecture. But the point of these Bell inequalities are they're a test you could actually run in the lab to convince yourself that nature really does allow entanglement. Okay, and nowadays, for many years there were experiments beginning, I believe, with Alain Aspect in the 80s, I believe, that did these kind of Bell inequalities in the lab, right? To say, okay, we really believe that nature allows you to create entangled states. And in the last decade or so, they've been really very good Bell inequality tests in the lab that really kind of more or less close all these loopholes that people would complain about the previous experiments, saying, okay, well, this or this could have been the reason why this is what you saw in the lab. There would be some fairly quote unquote contrived explanations of this, is my understanding. But nowadays, the experiments are really that good that we can more or less close all these loopholes, that really nature does work this way. Okay. Okay, and the other thing I want to mention is that, even though people like Einstein in the 30s, they disliked this idea of entanglement, nowadays, we have proofs that if you don't have entanglement in your system, especially for pure state computation, if the entanglement does not grow exponentially quickly with the size of the system, then you could simulate that quantum computation classically. Okay, so in particular, this means that if you want to exponentially outperform classical computers, then you have to have an amount of entanglement in your system which grows exponentially with the system size. Okay, so entanglement becomes a very, very important resource. Okay, so that's all I want to say about the history of entanglement. Let's start by talking about bipartite entanglement, and that's really all we'll talk about in this course. You could talk about bipartite means two parties. That's already difficult, but beyond that, you get into multi-party entanglement, and that's even orders of magnitude more difficult. Okay, so you can't even hope to characterize all the different types of entanglement there, in any nice sense at least. Okay, so let's talk about bipartite entanglement. Bipartite entanglement. Okay, so between two parties. Okay, so here you imagine, of course, you've got, let's say, Alice and Bob. Here they are, and the idea is that they're each supposed to share. Here's Alice, here's Bob. They're each supposed to share, one half of a state. Maybe that state could be a Bell state or whatever you like. Yep. Okay, so more generally, we're going to say, so let okay, so let psi be a two-party state. So again, it's going to act on, you can use indices 1, 2, or AB for Alice and Bob if you feel like it. It doesn't really matter. Okay, so this is a state that lives in CD1 tensor CD2. Okay, so the local dimensions, of course, don't have to match. Usually we like to think of D1 and D2 as being qubits. Okay, and so recall from the previous lecture, we said that psi AB is entangled if there do not exist, okay, I'll be consistent with my notes, right? Well, okay, let me write it a little bit, let me write it using a positive quantifier, if you will, if for all states psi1 in the first space, for all psi2 in the second space, okay, their tensor product, psi1 tensor psi2, does not equal to psi, okay, AB. Okay, so basically there's no way to factorize your state, okay, in terms of two individual states on each of the component systems. Okay, so we already said this earlier, so let's very quickly confirm now that the Bell state is indeed entangled, right? I've been kind of throwing this around, this claim, but let's prove it, okay? Okay, so this is my claim. Let's just quickly prove it. Okay, so again, we're going to do a proof by contradiction, right? If you want to claim that something does not exist, like here we're saying that, these things don't exist. For all states psi1 and psi2, you cannot make this work. the natural proof technique is contradiction, right? You assume it does exist and then show that something funny happens. So let's assume that these states do exist, okay? So assume psi 1, and let me just write it. So we're working on a 2-qubit space, right? So I'm just going to assume that my states look like this, right? It's going to be alpha 1, 0. I only need 2 basis vectors. That's why I'm mentioning this, right? So this is in C2, psi 2, alpha 2, 0, plus beta 2, 1. Okay, so assume I have these two states, and these guys satisfy this claim that if I take their tensor product, right, I get the Bell state back. Okay, so assume this is true. Sorry, I violated my own mantra, which is, we always want to state what proof technique we're using. So proof by contradiction. Okay, good. Okay, so what are we going to do? We're just going to basically expand left and right side out, if you will. So here I have an equation, right? I'm going to expand the left and the right side out, and I'm just going to observe that, it's impossible in general to fulfill this criteria. Okay. Okay, so on the left-hand side, right, here's this. Let's just expand this out, right? This is alpha 1, 0, plus beta 1, 1, right? Tensor alpha 2, 0, plus beta 2, 1. Okay, so let's expand this out. So again, you're going to have four cross terms, right? So I'm going to combine first these two and then these two, right? And then I'm going to combine these two and these two. Okay, so again, for the first time, I'll do this explicitly, but moving forward, I'll kind of skip some steps. But let me just do this one explicitly, just so you get comfortable. So this is the first 0 terms paired together, right? And then I have alpha 1, beta 2, 0, 1, plus beta 1, alpha 2, 1, 0, plus beta 1, beta 2, 1, 1. Okay, so these are all these 4 arrows basically. So the first one, the zeros paired together, alpha 1, alpha 2, and that's precisely what this is here. Okay, and again, I'm dropping the tensor product notation because this is standard. Okay, it just keeps it same. Okay, so that's left-hand side. Right-hand side is supposed to equal to what, right? This is supposed to equal to this thing, right? So this the left-hand side, this the right-hand side. Okay, this is supposed to just equal to this, right? 0, 0, plus 1 over 2, 1, 1. Okay, that's the claim. Okay, now, these 4 are basis, right? This is the standard basis for C4. You see this thing over here? This is the standard basis for C4. And so these 4 things are orthonormal, and that means that the only way that these two equations could hold, so this equality can hold, is that, all these coefficients have to line up, right? So for example, alpha 1, alpha 2 has to equal to 1 over root 2, right? And the ones we're actually going to focus on are these middle terms, right? Because the Bell state doesn't have the middle terms, the cross terms basically. And so this means that from this we can conclude that alpha 1, alpha 2, alpha 1, beta 2 has to equal to 0, okay? Which is this term over here. And now, we're working over the complex numbers, so the only way, this product can be equal to 0 is if either alpha 1 or alpha 2 or beta 2 is 0, right? At least one of them, okay? So let's suppose, okay, and whenever I write this thing, it always stands for without loss of generality. Okay, so that just means that, I'm making an assumption, for example. I'm going to assume, for example, for now that beta 2 is 0, but I could have just as well set alpha 1 equals to 0 and done an analogous argument, right? So I don't want to run through all the cases one by one. So I don't lose any generality by restricting to the case that beta 2 equals to 0. Okay, so therefore this product is 0. Okay. And so that takes care of this term, right? So then this product really is 0, but now I also have to worry about this one, right? But we also need now, what do we need? Well, we need beta 1, alpha 2 equals to 0, right? Okay, and So that's just coming from this term. Okay. So now what can I do, right? Again, either beta 1 or alpha 2 has to be equal to 0. Can I set beta 1 to 0? So note, we can't set beta 1 equals to 0. So why not? Why can I not set, sorry, what I meant to say first is not beta 1, sorry, but alpha 2, right? Why can I not set alpha 2 equals to 0? Right, so there are two terms here. Why can I not set this to 0? So what else have I set to 0? Beta 2, right? And where did these two come from? These two came from my state psi 2, right? They're the two coefficients. And if I set them both equal to 0, well then psi 2 is not a unit vector, it's the scalar 0, right? So that already is a contradiction. So the only option I have at this point is I have to set beta 1 to 0. That's my only option. Okay, so what just happened now is that I set beta 1 and beta 2 to be 0, right? So here, let me give these guys names. That's star and star star. So star and star star, they imply, oh, I'm terrible at drawing. They imply that, therefore, psi 1, this is up here. I set beta 1 to 0, so psi 1, alpha 1 therefore has to be 1, it's a unit vector. And likewise for psi 2. Both of these guys, the beta terms I set to 0, so they're both just the state 0, 0. And what does that mean? Therefore, that means that the tensor product of these two is nothing other than 0, 0, right? But, I claimed right here, right, that the tensor product wasn't supposed to equal to the Bell state, right? Not 0, 0. Okay, so this is a contradiction, right? This is not equal to the Bell state. I'm missing all the terms other than 0, 0, right? I'm missing these three terms. Okay, so therefore I have a contradiction, and this ends the proof. Okay, so the Bell state is indeed entanglement under this definition I've given you, that entanglement means you cannot factorize a state into its components, okay, into a tensor product of two single qubit states. Okay, so that's a simple example. And of course, it's a bit painful to go through that kind of proof technique every time, right? To sit down and write out these equations and take inner products. And the question is whether there's a more systematic way of telling if a state is entangled. Okay, and there is a more elegant tool. It's called the Schmidt Decomposition. So last time we talked about the spectral decomposition. Okay, I believe that was even in lecture 1. So now we'll talk about another type of decomposition that also starts with S. It's the Schmidt decomposition. It's actually related, but it's not the same. Okay. So here's the question: how to tell if a state psi, and this is in let's just assume our spaces both have the same dimension, is entangled. And here's the answer. We're going to go via this thing called the Schmidt decomposition. All right, so let's do it. All right. Okay, so, in this discussion, I'm just going to focus on qubits, but you could straightforwardly extend this definition to higher dimensional systems. The basic idea is, well, yeah, okay, let me just stay with what I just said, right? The basic idea is that if I have a 2-qubit pure state, I can always write it in a very special form, okay, using this decomposition, right? And the idea is that, any state psi, and this is again a 2-qubit state, so it lives in C2 tensor C2, okay, can be written. How do I write it? Well, I write it like this. Psi equals to alpha 0, A0, B0, plus alpha 1, oops, A1, B1. Okay, and of course I have to tell you the properties of all these terms, right? Otherwise it's not so interesting. So let me tell you what are the properties, right? Where these guys here, right? These are the scalars, right? These are called the Schmidt coefficients. Schmidt coefficients. So where the Schmidt coefficients they're both real and they're non-negative, satisfy alpha 0, alpha 1 are in the reals, alpha 0, alpha 1 are greater than or equal to 0. Okay, so they're both non-negative real numbers actually, but so this is a departure from our usual representations where the coefficients are generally allowed to be complex. Okay, so two things. So number one and number two is that these things here, right? These are called the Schmitt vectors. Okay, so the Schmitt vectors. Okay, so I have a pair of them, right? I mean, so I have A0, A1 on the first system. A0, A1. And I have a second set, right, which is on the second system, B0, B1. And the key property here is that these are orthonormal bases. Okay, so for example, A0, A1 could be just ket0, ket1, for example. Okay. Now, of course, this is a unit vector, right? So let's just do a sanity check. So because it's a unit vector, right, and because, these guys are orthonormal bases, then, the sum of the squares of these, so since the Schmitt vectors form orthonormal bases, what we conclude from that is that, this vector is orthogonal to this one, and therefore, in order for a side to be unit vector, this has to hold, the usual normalization condition, right? Okay, so you have to be a little bit careful, if these vectors were not orthonormal to each other, then, they could have some overlap, and then, the sum of the squares of the amplitudes don't have to sum to 1 anymore, right? Because some of the overlap between these two vectors would kind of account for that lack of normalization condition. Okay, and what I want to say, the third definition I want to say is that the Schmidt rank, which is very important for us, the Schmidt rank of psi is the number of non-zero, okay, so this is important, Schmidt coefficients. Okay, so it's the number of these alpha 0 and alpha 1 which are non-zero. Good. So let's just do a quick example, right? Just to make sure we're understanding what's going on. Let's look at the Bell state. Okay. So what is the Schmidt decomposition of the Bell state? All right, take a moment to stare at this thing. What is the Schmidt decomposition of the Bell state? Okay, so what did I want? I wanted the amplitudes to be non-negative real, which they are, right? And I needed, the states on the first system, A0, A1, I needed those to be a basis. And here they're ket0 and ket1, so they're a basis. And likewise on B, ket0, ket1, that's also a basis, right? So this is already the Schmidt decomposition. Okay, you kind of get that for free in this case. This is already the Schmidt decomposition of phi plus, right? The very way I've written it, that is the Schmidt decomposition. Okay, so what I want you to notice here is that the Schmidt rank of this thing, the number of non-zero terms it has are 2, right? There are 2 terms, 2 non-zero amplitudes. Sorry. Okay. And let's do another example quickly. right? If I instead look at just this state, 0, 0, right? This is in C2. Okay, so what is the Schmidt decomposition of this thing? Okay, think about it for a second. Okay, so the Schmidt decomposition of this thing, right? Well, let's see, right? Where are the Schmidt coefficients? Well, you know, there's one right here in front, right? It's hiding. It's just the scalar 1. That's non-negative. And the second Schmidt coefficient technically is a 0, right? I don't need to write it down. Okay, and so in particular, you know, let me be a little bit more formal here. I could always write this as 1 times 0, 0 plus 0 times 1, 1, for example, right? And so in this sense, I can think of this as already being in its Schmidt decomposition. Okay, right? Because, you know, this is certainly kind of, you know, this is a basis. 0, 0, and 1, 1 is a basis on party 1. Okay, and so the Schmidt rank of this thing, what is that? Well, there's only one non-zero term here, right? So this term is a non-zero, and in this term, whatever other term I could have added here, I chose 1, 1, you know, there's a 0 in front. So the Schmidt rank of this is 1. And, you know, by definition, of course, note that 0, 0, you know, it just literally is this, right? So by definition, this is not entangled, right? It's a tensor product of two constituent states, right? Okay, so here, you know, you scratch your head a little bit and you say, huh, well, isn't that funny, right? You know, a non-entangled state had Schmidt rank 1 and an entangled state had Schmidt rank 2. Is there anything more to the story, right? Okay, and indeed, that's exactly the full story for bipartite pure states. That is exactly the full story. And I'm very careful to say for bipartite pure states, because if you go to more than 2 parties, or if you go to mixed states, which we'll do later today, you know, the story changes dramatically. Okay, so the lesson here, I haven't proved it, of course, but, you know, this is actually a fact that we'll just take, right? For bipartite pure states, psi, right, which acts in, you know, CD, tensor CD, more generally. Psi is entangled if and only if the Schmidt rank of psi is strictly larger than 1. Okay, and so this is just my notation henceforth for Schmidt rank. Okay, so one way to figure out if your state is entangled is to write it in the Schmidt decomposition then, and just see how many non-zero coefficients you have. That's it. Now, of course, I'm saying that's it. I'm waving my hands because I didn't actually tell you how to compute the Schmidt decomposition. It turns out that you can do it in polynomial time. Okay, so we won't really go through that in this course. We'll talk more about it a bit later, but we won't go through it very thoroughly. For now, suffice to say that, you know, one can write down the Schmidt decomposition of a pure bipartite state in polynomial time. Okay, good. Okay, so this is kind of like the situation with the spectral decomposition where, you know, I didn't really give you a very good technique for coming up with the spectral decomposition. I mean, sure, you could, you know, write down the characteristic equation and solve for the eigenvalues and so forth, but, you know, we're not realistically going to do that in this course. And the same thing for the spectral decomposition. With the Schmidt decomposition also, you know, we're not going to compute the Schmidt decomposition too often, but it turns out to be very useful as a proof technique that, you know, if you want to prove something about a bipartite pure state, it's usually helpful to start by writing it in terms of its Schmidt decomposition, just like you did with the spectral decomposition. So let me just make an observation here to close our discussion of the Schmidt decomposition. So, you know, what's kind of special about the Schmidt decomposition, other than, you know, it tells us about this entangled or not? You know, in general, I could always write my state psi as a sum over tensor products. You know, that's what this is. It's a sum over tensor products. I could always do that, right? So, you know, if you think back, for example, to just remaining in the 2 qubits setting, but you can generalize this to higher dimensions, right? You know, you could always write, psi using at most 4 terms, right? In terms of the standard basis, which is also a product basis, right? It's just a tensor product of individual single qubit standard basis states. Right? I could have always done this expansion too, right? There's nothing wrong with this expansion. Okay? And just like before, I mean, you know, the states I'm putting on the first qubit, they're an orthonormal basis, for example, just like for the Schmidt decomposition. So what is the key difference between, you know, this standard basis expansion and this one here? Well, you know, there are 2 differences. The first is that, you know, the coefficients are all non-negative real for the Schmidt decomposition. Here they're complex. And perhaps more interestingly is the fact that, you know, here in general, I really needed to write down 4 different states. We're in C4. Whereas with the Schmidt decomposition, I get by with just 2. Okay, writing down 2 states. So more generally, let me just be clear that, you know, if I have a state psi in higher dimensions, so CD1 tensor CD2 can be written via the Schmidt decomposition. How does this work? It's just going to be the psi equals to the sum over, you know, I of, let me just call it alpha I. And here I'm just going to have, you know, a basis here and a basis here. And, you know, the key points here is that, you know, of course, these guys are the Schmidt coefficients. These are all non-negative real. And this thing goes over. Normally, with the standard basis decomposition, I would expect to have one term in this expansion for every way of pairing together the bases for the individual spaces. So I'd normally expect to have D1 times D2 terms in this expansion. But in the Schmidt decomposition, I get by with just the minimum of D1 and D2. So whichever one is the smallest, the smaller dimension, that's the number of terms in this expansion. It's much smaller. It's quadratically smaller than the full expansion for state in the standard basis. Okay, so that's the last thing I want to tell you about the Schmidt decomposition. Okay, good. So this allows us to move on to our next topic in this lecture, which is density operators, right? So we've said that a quantum state, a bipartite quantum pure state, is entangled if and only if its Schmidt rank is at least 2, right? But let's take a moment, a step back, right? And let's take a look at the bigger picture, right? What was the goal of this lecture, right? One of the goals of this lecture was to think about, you know, if I have an entangled state across 2 parties, right? Then, you know, we said in a previous lecture that there's this idea that, you know, in the classical world, if I have, say, you know, a pair of birds, let's say, and they're, let's say, really good friends, and, you know, they always go everywhere together, you know, you could always still describe any individual bird on its own of the pair, right? I mean, it's totally well defined, and, you know, there's no uncertainty about this. You know exactly what each bird looks like at all times, right? But if you had a pair of, say, quantum particles, right, and they're entangled, it turns out this is not generally the case anymore. Like, you cannot describe fully with full certainty what each particle is up to, okay? And so in particular, we need to have a way to describe quantum states that inherently has some notion of uncertainty built into it. Okay, and I don't mean like uncertainty induced by measurement. I mean just no uncertainty in the sense that we don't exactly even know what state our system is in, right? When I talk about pure states, I know exactly my system is in this vector, right? This is the state. If I measure, of course, then I'll get some probabilities coming out of that, but that's a different story. Now I'm saying I don't even know exactly which state my system is in to begin with, okay? Never mind the measurement part. So that's going to be the so-called density operator formalism, which is what I've written here. Okay, and so, you know, the driving question, if you will, right, is, you know, how to describe the state. Oh, sorry, let me actually call it what I will call it throughout the rest of the talk, which is the so-called reduced state of the Bell state, right? So this acts on, you know, Alice Bob on, say, party A. Right, on Alice's side. So how do we describe that? I'd like some sort of mathematical description, right? I can't just wave my hand and say, oh yeah, the state exists, right? You know, I want some formal description. Okay, so now this brings us into the world of pure versus mixed states, right? And that's where density operators are going to come from. And what we're going to see in the process is that you should really think of quantum states ultimately as generalizing classical probability distributions. Okay, and I'll be more formal in a second. Okay, so thus far, what have we done thus far? Okay, so thus far, what did we say? We said that a d-dimensional quantum state psi is in CD. That's basically what we've been, preaching this whole time, right? Good. So there's nothing false about that. This is true. And the name we give to these guys henceforth, I've sort of said this over and over again, right? But this is a pure state. A pure state is basically going to be, I'll define it right now, a rank 1 density operator. But like I said, I haven't defined a density operator yet. So when I define density operators later, you can come back and look at this and say, oh, it's a rank 1 density operator, right? That's a pure state. Okay? Good. And so the important thing here is that we know that our system is in precisely the state psi. Okay, so I know my system. This is the value of the system, right? Period. It's psi. Again, if I measure it, yes, some distribution will come out. That's a different story, right? That's the measurement process. It's not about uncertainty of what state I actually have. Okay, so here's kind of the motivating question, right? How do we model randomness, right? Say, example, a coin flip. Right? Because, the analogous thing for a pure state would be to say that, a classical pure state, it's well defined, would be example, 0 or 1, right? Okay, so you literally, ket 0 is a pure state, ket 1 is a pure state, and those mean that, your coin, for example, it's heads or tails, right? It's not, there's no randomness involved here. You're just telling me what is the state of the coin, right? But now I want to have this idea that, I'm going to flip a coin, and with probability half, I'm going to get heads, and probably half, I'm going to get tails, right? And I can play the same game with quantum states, right? I can say, okay, maybe I have a number of states at my disposal, maybe 0 and 1, for example, heads or tails, if you will. And I'm going to say I'm going to, flip a coin, and if it comes up heads, I'm going to prepare one quantum state, and if it comes up tails, I'm going to prepare some other quantum state. How do I write down the description of that funny randomized construction, right? And that's what this density operator formalism is used for, right? So, okay, so here's the idea. So obviously we're going to use density operators. And again, I'm going to have to define this. I haven't defined it yet. So what do? We say, suppose we play this game, with probability a half. I prepare, say 0. And with probability a half, and maybe you can think of this as heads if you like. Heads. With probability a half, we prepare 1, which is tails. Right? And the way we describe then, this randomized mixture is going to be not as a vector, but actually as a matrix, right? So the state, the corresponding density operator, okay? And the point here, sorry, let me really stress here, right? So let me say, imagine that I prepare the state. I prepare it, okay? And the point is that you don't know which one I prepared. Okay, so it's very important, right? Because if you know that I prepared ket 0, then your view of the system is a pure state. It's just 0. You know it's 0, right? But the point is that if I don't tell you the outcome of the coin flip, and I just hand you this quantum system, right, that you don't know what it is without doing a measurement, you have no way of knowing. Like your knowledge at this point is completely random. It looks like, with probably 50, it looks like 0, and probably 50, it looks like 1, right? So the question is, for you, what, or not what, but how do we describe your state of knowledge about what I prepared? Okay, again, I really want to stress, like, this is just like Schrodinger's cat, right? Before you open the box, right, you have no idea what's happened, right? You've done a measure, well, okay, that's a bit different, I guess, because they were assuming things were a pure state, and there was no, sorry, I take that back. It's not Schrodinger's cat, and, think about for a second why this is not Schrodinger's cat, right? In Schrodinger's cat, we said that the input is a superposition of 0 and 1, right? Whereas here I'm flipping a coin. This is a randomized process. It's something different. Okay, so the answer is that, for density operators, we tend to use this rho notation. And the way you write this down is you take the two states you could have prepared and you write them in this ket-bra form. You make a matrix out of it. So I'll take these two. And to specify that with probability half I got each one, I would put a half in front of here and a half in front of here. Okay, and this would be the density operator describing your knowledge, your state of knowledge about the system. Okay? So, that's the way I want you to think about density operators. And, we'll give a formal description as to, how do you mathematically characterize them. So, more generally, so suppose I prepare one of, some set of states. Notice how these states do not need to be orthonormal. Okay, they can be any set of states in the world. Okay, so I prepare some set of states indexed by I, right? Maybe up to, some number n, it doesn't matter. Again, n has nothing to do with the dimension, right? You can prepare as many as you like, okay? Where the probability of preparing psi I is equal to, some pi, right? And of course, let me be clear, if I sum up the probabilities, they should sum to 1, right? So from 1 up to n, obviously these things should sum to 1. It's a distribution. Okay, so more generally, we can play this experiment. And then the density operator that describes your state of knowledge, right? If you don't know which I chose at random, right, is rho, the sum over I equal to 1 up to n of psi I, and we just put the probability distribution in front. Right, I'll do this in red. Pi. Okay, that's a density operator. Okay, and so we call these mixed states instead of pure. And why? It's because you don't know which of the states psi I you have in your possession. That's why. Okay. If you knew what it was, it would be called the pure state. Sorry, since you don't know. Okay, because you don't know which one I gave you. Okay, so that's in a very quick nutshell to begin with, the density operator formalism, and let's digest it a bit now. So let's make two observations here and really try and understand the difference between a density operator and a pure state, right? Because I've given you kind of like this thought process, thought experiment, if you will, for how these density operators come about. Let's understand their mathematical structure a little bit. Okay, so observations. Okay, so first, let's talk about mixtures versus superpositions. Okay. Okay, so this thing on the left, well, okay, superpositions are a sum of vectors, just in the very basic algebraic formalism, right? That's what we've been doing so far. And mixtures, if you'll notice, I mean, these guys are each this thing over here, it's a linear operator that acts on whatever dimension these vectors live in, right? If they live in, say, CD, right? It's a linear operator that acts on CD. It's a matrix, right? It's not a vector anymore. So mixtures are a sum of matrices now, not vectors. Okay, and here we have total knowledge of the state. All right. Whereas here we have only partial knowledge of the state, right? Only partial knowledge, okay? We don't know exactly which state in the mixture we have, right? Okay, so that's the very first high-level difference between these two. Okay, and the other one is that, yeah, so let me just revisit. I made a comment above that, these pure states are nothing other than, here, I said a pure state is a rank 1 density operator, so let me clarify what I mean by that. Okay, pure states. Okay, so if there's only one state in the mixture, okay, by which I mean I could write rho as just psi psi. Okay, there's only one term, there's nothing else in the sum. Okay, so in other words, you can think of this as, pi equals to 1. So, here we had a bunch of probabilities we added, right? If one of them is a 1, it's a singleton distribution, and everything else is 0, then you get a pure state. So we say at that point that rho is pure. So notice how I wrote rho is pure, the density operator, and then I might as well just refer to it as psi. And it's also a rank 1 operator. As a matrix, it's rank 1. Right, and you could see this just because there's only one term. This is a spectral decomposition, right? You're staring at it. It's psi, ket bra psi, and that's it. There's nothing else in the sum. So this is one of the eigenvectors of the eigenvalue 1, and that's their state. It's rank 1. Okay, it's only got one eigenvalue that's non-zero. Okay, and that's the density matrix right here. So let's just do a very quick concrete example to understand the difference between mixtures and superpositions. Okay. So let's do an example. So if I think about the density matrix rho equals to a half 0 0 plus a half 1 1, right? What is this thing? Okay, so think back, what was this? I remember when we said we had ket I broad j, that was just you take a matrix and you just put a 1 in the position at row column ij. So this is nothing other than a half, and we put a 1 in the top left because it's at index 0 0, right? Index 0 0 is top left, plus a half, and index 1 1 next puts a 1 in the bottom right. And so when I add these two, I just basically get this, right? I get the identity times a half, right? Okay, that's exactly what we get. So this is what models a coin flip, right? A coin flip is with probability half, right? I prepared 0, or say heads, and with probability half, I prepared 1, right? And it turns out the right density operator to describe that is essentially the identity matrix up to normalization. Okay, and we'll see why the normalization is important shortly. Okay, and the identity matrix plays a very special role here, and we'll also visit that in a second. Let me not stray too far from the point I wanted to make here, which is that now let's take the same thing, 0 and 1, but show you what the superposition looks like. A note here, by the way, that this thing here is a linear operator on C2. Okay, so it's a 2 by 2 matrix. So density matrix is a matrix, as the name suggests. Okay, so how about the state vector, or the pure pure state vector? That looks, let's say, most similar superficially might be this, right? 1 over root 2, 0, plus 1 over root 2, 1. So the point is both of these are kind of equally weighted versions of ket 0, ket 1, right? And well, what is this thing? Well, we've already said that this is equal to, 1, 1, which is just the plus state. And now this thing, where does this live? Well, this thing lives in C2, right? It's a vector. It's not a matrix, right? So do compare, this expression with this one. See, like we're missing the L, right? Okay. Good. So let me take a quick moment just to do part of the next exercise, just to slowly get you comfortable with writing density matrices. Okay, so whenever I give you a pure state, I say, what is the density matrix for this? It's easy as pie. This is the idea, right? This is how you do it. So given, let's say, some state alpha 0 plus beta 1, let's do working over qubits. Its density operator is, you can think of this. Well, first let me write it down. It's just this, right? It's rho equals to psi psi. So first, why? Why is this the right density operator? Think about it for a second. I have my coffee and tea lined up here, so I'm well hydrated at all times. Okay, so the reason why is because it fits into that previous thought experiment, right? This is a scenario where you know exactly what your state is. Your state is exactly psi, right? And so this is a game where you flip a biased coin. The coin comes up, heads, let's say with probability 1. And when you get heads, you prepare this state, right? And with probability 0, it comes up tails, in which case you prepare some other state. But we don't care what that other state is because, we're never going to prepare it, right? So if you think about that thought experiment, this is the corresponding density matrix under the definition I already gave you. And now we just plug in the definition, right? On the left, we have alpha 0 plus beta 1. On the right, we have to take a dagger, so alpha 0, beta star 1, okay? And now we just expand, right? I'm going to get 4 terms. Okay? And the first term is just going to be, remember you paired together, I'll just show you for the very first one, right? You pair together the first two and you get alpha squared. Then we'll get alpha beta star plus alpha star beta plus absolute value beta squared. Okay, so if you want to draw this as a 2 by 2 matrix, it looks like absolute value of alpha squared, absolute value beta squared, alpha beta star, alpha star beta. Okay, so in general, for a single qubit density operator, this is what it would look like, okay, in terms of its amplitudes. Okay, so in the future, whenever I say, here's a pure state, what is its density operator? You always do the same thing. Just take the rank 1 projector onto that state. Okay, good. So this was a very kind of, I don't want to say hand wavy, it's more like an operational way to define the density operator, right? We played this thought experiment where, you flip a coin with some probability you prepare one state or another state, right? But what is the mathematical characterization of these states? Like when you do that kind of thought experiment, what class of operators pops out, right? And that's really how I'm going to properly define a density operator now, formally speaking. Okay, so formal definition. Density operator. Okay, so a matrix rho, and rho is just, again, the standard notation we use. It's going to need to be square, okay? So that's why it maps CD back to itself. Okay, so a matrix or a linear operator rho, more general, well, not equivalently, is a density matrix or density operator if two things hold, right? So the first thing I need is that rho is positive semi-definite, okay, which in particular meant that it's Hermitian, okay, and its eigenvalues are non-negative, right? So remember that this meant that rho is positive semi-definite. So remember I told you last class that we introduced all these operators when we started that lecture, and I said we're going to need them beyond measurements, and indeed here we're using this PSD class. Okay, so remember what this meant is that it's Hermitian, okay, which meant its eigenvalues are real. But not only that, it has only non-negative real eigenvalues. Okay, good. Okay, so that's the first condition. The second one, and let me be clear, let me put an and here to be clear that both have to hold. The next thing we need is that the trace of rho has to be 1. Okay, and just to remind you, oops, rho has, this TR is the trace operator. Okay, so rho has trace 1. Okay, so this is the formal characterization of what we shall mean as density operators throughout this course. One way to motivate them is via that thought experiment, which we talked about, and we're actually going to revisit that in just a second, okay, to see why exactly this captures that thought experiment. Okay, but just as a sanity check, right? Whenever you learn something new, always do a sanity check, make sure, apply it to an example you know to make sure you really understand what's happening, right? So let's check that the operators we've been talking about satisfy these two conditions. Okay, so let's in particular look at well, let's do something like this. Let's suppose rho equals to something like what we did in our thought experiment, right? With probability half, I prepare psi 1. With probability half, I prepare psi 2. Okay, and I claim this is a density operator. So why is that true? So first, let's check, right? Is rho positive semi-definite, right? So is rho positive semi-definite? Okay, and the answer is yes. There are two ways to see that. One way is to do it directly. Here I'm just going to kind of leverage a fact, but it's very easy to prove this fact, which is that if I have two positive operators, okay, A and B, then their sum is also positive. Okay? So let me put in a red mark. Caution. It might be tempting to say that also, assuming A and B are positive, that the product is positive. And this is false. In general. This is in general false. Okay? It's true if they diagonalize on the same basis, but in general it's false. Okay? So be very careful about that. Let's see. How do you prove this? Right? Let's see. Can you think about how you want to prove this? Let's not do the full thing, but you know, what characterization of being positive would you use? Maybe that's really what I want to get at. Well, what you want to do is the idea that you want to use the characterization that A plus B is going to be positive semi-definite if and only if for all psi of A plus B, psi is greater than or equal to 0. Okay, so, and at this point it's just straightforward expansion of you know, the terms you see here. Okay, and just remembering what the definition of being positive is. Okay, so I won't complete that proof, it's just like another line, so I'll leave that to you as a nice exercise. So my point was that I wanted to prove that this thing was positive. Sorry, let me put both these conditions here. So I wanted to prove this first condition, that rho is positive. Okay, and in particular, you know, rho is a sum of two positive operators because, you know, this is just the rank 1 projection onto state psi 1. And in the next exercise, you will show that in the notes, there's an exercise that says that, you know, prove that psi is positive semi-definite. You know, for any psi, it doesn't really matter which one you take, right? And again, you want to use precisely this characterization of being PSD. Okay, so again, feel free to pause the video and try this out. Okay, so therefore, you know, if you believe that each of these guys are positive, right? So any rank 1 any projection is positive by definition, right? Well, I mean, I guess that's another way of seeing it, right? I mean, you can prove it directly, but at the same time, you know, we define positive operators as being Hermitian and having 0, 1 eigenvalues. So by definition, they have all real eigenvalues, which are 0 and 1. We talked about this last class. And so by definition, they're also positive semi-definite. They're a very special class of positive semi-definite operators. But you can also prove it directly. Okay, so these two guys are positive, and now you have a non-negative sum. And I should be careful here. I mean, you have the, here I really just have a straight sum, right? I'm not putting in any like minuses or anything like that. It really should be a plus. So then, you know, the sum of them will also be positive by this fact, right? So by this thing here, rho is positive semi-definite. Okay. Okay, good. So the first property holds, that rho is positive semi-definite. And then we just need to check the trace. Is the trace of rho 1? So let's just compute the trace. The trace of rho is equal to, and remember the trace is a linear operator, so I could just pull out all the constants. Okay. And now, you know, each of these is a rank 1 projector. There are pure states, unit vectors, so by the cyclicity of the trace, I can move this around, and they will each have trace 1, and I'll get a half plus a half, which equals 1. Okay. So indeed, this is indeed a density operator. Okay, so that passes our sanity check. Now, this is the formal definition for what a density operator is, and now you might ask, okay, what is the connection between this thing and this thought experiment we described a couple of minutes ago? Okay, so let's go backwards now and see, you know, how these two fit together. So question, what is the connection between the formal characterization and the thought experiment? Good. So what is that characterization? Well, you know, let's see this, right? Remember we said that a density operator rho satisfies rho is PSD, and the trace of rho is 1, right? So if rho is PSD, right, so what can I do? That means I can take the spectral decomposition, okay, and, you know, I'm just going to write it down in an abstract form, right? Of course, I don't know what the eigenvalues are, lambda I, and then I have the eigenvectors, lambda I, ket bra. Okay, so that's a spectral decomposition, and the point is that because it's positive semi-definite, what do we know? Well, we know that these things are non-negative real numbers, right? The eigenvalues are non-negative reals. So that's what the first condition buys us. And now I also know that these things, the trace is 1, right? And we saw in the first lecture that if I take the trace of an operator and you write that operator in the spectral decomposition, the trace of the operator gives you back the sum of the eigenvalues. So let's use that here. Okay, so if the trace of rho is 1, well, that means that the sum of the eigenvalues of rho, sum over lambda I, equals to 1. Okay, so I have these two properties here, right? I have a set of real numbers, which are all non-negative, and they sum to 1. So what is that? Well, that's just a probability distribution. Okay. Ta-da, right? That's it. So you can view this thing, one way to view it, and you should be a little bit careful in terms of this view because the spectral decomposition for rho is not necessarily unique in general, right? So we mentioned earlier that if any of the eigenvalues is not unique, it shows up more than once, then the spectral decomposition, there are an uncountable number of spectral decompositions basically in that degenerate subspace, right? I think that's right? Certainly it's not unique anymore. Yeah, so, but the point here is that you can think of this as this thing is diagonalizing in the standard basis, and, sorry, not in the standard, in this basis lambda I, and you could think of it as a thought experiment where with probability lambda I, we just said it's a distribution, you prepare the state lambda I, ket lambda I, okay? So that is exactly how our thought experiment went. That's the link, okay? So in this sense, by the way, quantum states. So density operators are kind of the most general description you can have, at least at the level of this course. And quantum states are essentially just probability distributions, right? If these guys were all the standard basis, then that's like saying you would be putting these guys on the diagonal. You'd have some classical distribution on the diagonal, right? What's the difference between this thing here and a classical distribution? Well, this is just a classical distribution. The only thing that's different is that this basis here, this eigenbasis, is not necessarily the standard basis, right? You're allowed to rotate your system to be in some funny other basis. That's what makes it quantum, essentially, okay? And that rotation itself, of course, is what allows you to introduce things like entanglement between the subsystems. Okay. So we defined density operators. And of course, we have a very special density operator, one we really love. Well, not really, I guess. Maybe you love it. Okay, and that's the maximally mixed state, which is just the identity, basically. Which you already saw, right? When we took the Bell state and we... wait, where did we do that? Sorry, we didn't do that part yet. No, when we took this thing here, the mixture of 0 and 1, right, we got the identity out. Where did I put that? Here, right? So we already saw this identity state, and it's going to come up again. So let me give you some motivation as to why we care about this state. Like, what is it supposed to mean? Like, how should you interpret this thing, right? So maximally mixed state, here it is. Okay. And what is this? This is nothing other than rho equals to the identity, and it's normalized by the dimension because I'm going to assume that the identity is acting on CD. Okay, so that's where this D is coming from. So, please note, this is a matrix up top, and normally we write it this way. It's kind of abusing notation. This is a scalar on the bottom, right? That's the normalization. So, equivalently, or more accurately, one should write this, but, it's just easier to write it as a fraction. Okay, and that's fairly standard. Okay, so let's just check that this is a positive, so this is a density operator, right? Is it positive semi-definite? Well, what are the eigenvalues of identity? It's certainly Hermitian, right? It's diagonal, so all its eigenvalues are sitting on the diagonal, and they're all 1, all right? And then, of course, over D because of this normalization. So indeed, rho is positive semi-definite. And the other condition we needed for a density operator was the trace condition. So let's just check. So first, rho is PSD, since identity has all eigenvalues being 1. Okay. And the trace of rho, what is that? Again, it's a linear operator, so I could pull out the 1 over D, and then just take the trace of the identity. And the identity just has D ones on the diagonal, so the trace is just D. Right, so it's D over D, which is 1. Okay, so this is indeed, a valid quantum density operator. Okay, now the question is, what in the world does this thing actually represent? So what is the meaning? Okay, so what does identity over D represent? Okay. And so to kind of get intuition, let's go back always. Whenever you're learning something for the first time, right, you try the concept on an example that you already understand well. So let's go back to the coin flip, right? For the coin flip up here, over here, right, we said that we can model a coin flip by, a half 0 plus a half 1, and the density operator turned out to be identity over 2. So what should that mean? Well, a fair coin flip is a state of maximal ignorance, right? You know absolutely nothing about the coin. With equal probability, it's 0 or 1. And indeed, that's the way you should think of the identity, right? The maximally mixed state is a state of total ignorance. We know nothing about what state our quantum system is actually in. And how can we formalize that? Right? Because in particular, we're not in the classical world. In the classical world, there's a very special choice of basis. It's ket 0, ket 1, the standard basis. But in the quantum world, all bases are legal, right? They're fair game. So what does it mean to be in a state of maximal ignorance? So let me tell you, right? So the identity over D is a state of, maximal ignorance. Please don't use that as an insult against your friends. is a state of maximal ignorance if, sorry, it's not if, but because, right? Because, what can we say? Well, the identity, remember we said this earlier, right? The identity has this very special property that you can diagonalize it in the standard basis, right? But actually you could diagonalize it in any basis whatsoever, right? So I can always take I equals to 1 up to d, take your favorite basis, okay? And then for any orthonormal basis psi I. Okay, so it doesn't matter which one you want. The point is that the identity always diagonalizes in that basis, right? And so this is why we think about it as a state of maximal ignorance, right? You don't even know what basis you're working in some sense, if you're in an identity, right? Pick your favorite basis. It's like you, to prepare the maximally mixed state, you can pick any basis you like, take an orthonormal basis for that, take your favorite orthonormal basis, flip a coin, and uniformly at random prepare one of those states. Okay, so really, if you have the identity in your possession, you know absolutely nothing. Okay, any basis could have given rise to that state. Okay, so i.e. ID over D has thought experiment. Let's just be formal, or slightly more formal. 1, pick any orthonormal basis. Doesn't matter which one. Psi I. With probability 1 over D, prepare psi I. Okay? That's what the identity represents. So it's basically the quantum analog of the uniform distribution. Okay, and if you know anything about things like information theory, like entropy functions, which we may or may not do later in this course, just like the uniform distribution is the distribution with maximal uncertainty in the sense that it maximizes the entropy function, there's a notion of quantum entropy called the von Neumann entropy, and analogously, the identity operator or density operator I over D maximizes the von Neumann entropy. Okay, but for now, let's not worry too much about entropies. Good. All right, so we're ready to kind of put the nail in the coffin, if you will, for this lecture, in the sense that, we kind of have all our ingredients now. Now we can kind of hammer home the point we really wanted to get to. Well, we don't have all the ingredients, but we can make kind of like the last streak, let's say, if you will, or push. We need to pick up something called the partial trace operation. Right? Remember, the goal so far was we wanted to talk about what does half of an entangled state look like? How can you describe that system, right? And so now we have the density operator formalism at our disposal. Now the only question is that, I have my Bell state phi plus on AB, right? And, there's going to be some map that's going to take it to some density operator rho that acts on A, right? And I don't know what rho A looks like yet because I haven't specified what this map is yet, right? So the question is, what is the map that's going to kind of throw out half of phi plus for me? And that map is the partial trace operation. Okay, so in the great words of one of my esteemed teachers, John Watrous, you're going to take half the system and flush it down the toilet. Okay? So, okay, so what's the intuition? Let me write that down as well, intuition. So given a bipartite state, and I'm just going to write it as a density matrix, most generally, right? Because remember, any pure state can be written as a density matrix. So given any bipartite density operator rho AB, the partial trace tells you the reduced state on, say, system A. Okay, it doesn't matter. You could also say system B, right? Throws out one of the systems and tells you what the other system looks like. So, formally, right? So formally, what does this mean? So the partial trace, formally speaking, so let's talk about, let's suppose I just want the density operator on system A. Okay, so that means that I'm going to trace out system B. That's why I write this. So we trace out B, i.e. Bye-bye B. Okay, that's the one we flushed down the toilet. Okay. And this is a linear map, just like the regular trace, right? And what does it do? Well, what are the input and output spaces, right? So you start with the density operator, and this thing acts on a bipartite space. And I'm throwing out the second subsystem, so I should have something just on the first space, CD1. Okay, that's at least the formal specification of it, right? But I haven't told you the exact action of this map yet. Okay, so now how are we going to define the partial trace, right? So as you might guess, it has something to do with the trace, right? Except I'm not, I'm only going to apply it to one subsystem, not to the full thing like I normally would. So in order to kind of be motivated, or to motivate a definition, okay? I don't know how excited you can get about a partial trace, right? But let's do our best. Oh, that's a nice squiggly line I drew there, huh? All right, looks like a wave. So motivation, so normally the trace, right? If I write the trace of, say, row AB, right? Remember, this is the sum of the diagonal terms, right? So what does that mean? That means that I could write it like this, right? If I use the from I equals to 1 up to D, or technically we were starting at 0, right? Because our indexing for entries in the matrix started at 0, but it doesn't really matter. It looks like this, right? Row AB equals identity. Because remember that if I sandwich you with the same standard vector on both sides, II, that's just picking out the term of row on the II point on the diagonal. That's just the definition of the trace. So is the regular trace, or the full trace, right? That is not a formal term, by the way. Okay, so partial trace is going to be the exact same idea, except I'm only going to apply the trace on the subsystem I'm getting rid of, right? And think about it this way, right? What does the trace do? The trace takes this matrix and squishes it down into just a scalar, right? That's essentially like throwing out that big system, right? And replacing it just with one number. And now we're going to do the same thing with B, right? I'm going to take all of B and I'm going to squish it into a scalar so I can just toss it out, essentially. So therefore, the way I'll define the partial trace, and there's more than one way to do it equivalently. So now let's do partial trace. So now I say trace of, and notice how I'll put the B now, because I'm going to throw out system B. So same thing, right? I need to have a sum. So it's just like a trace. I should be a little bit careful here because I'm tracing out subsystem B, so the sum should depend on the dimension, right? So let me put a D2 here because I'm tracing out subsystem B. Here's row AB, right? And now the question is, how in the world do I say that I'm only tracing out system B and not system A? So whenever you want to act like the identity on a subsystem, then you put down the identity matrix, right? So what do? I put an identity on A, and I want to put a tensor, something on B, right? And what am I going to put on B? Well, I already told you how to do the trace, right here, right? We want to do the sandwiching with the standard basis vectors. And so if I do this, then intuitively, it certainly looks like I'm doing a trace only on the B subsystem, okay? And that's it, okay? So, if you want to be a little bit more clear as to how things can be bracketed, you can try this. Okay, so you'll notice how, on the A subsystem, we're hitting it with a matrix, so the dimension won't change of the A subsystem, but on the B subsystem, I've got a D by 1 column vector, right? So that's going to take the dimension down from D to a scalar, just like we want. Okay, so that's the partial trace, and now we're just going to do some exercises, okay? Now, with that said, I do want to tell you, as an aside, an equivalent definition of the partial trace. Usually I find it easier to work with this one, but they're both the same, really. So let's do an aside. an equivalent definition. Yeah, the nice thing about, well, let me write the definitions down, and then we'll say what's nice about each one. So what's an equivalent definition? You could have written it down as the trace out of B of row AB. Sorry. So the thing with this definition is you don't write it that way. It only, if you have row A tensor row B, right? So it's already in tensor product, then this just equals to row A times the scalar of row B, trace of row B. So notice how, you know, this is just a scalar. I mean, we know that rho is a density operator, so it's actually going to be 1, right, the trace. But more generally, you could apply it even to operators that aren't density operators. Okay, so this is an equivalent way to define the partial trace. So why is it an equivalent way? I mean, it's pretty clear to see that, you know, if you believe this if you take this definition, you could extract this equality, right? You just take the trace of this side. But the reverse is not as clear, let's say. If you're comfortable with things like linear algebra, then basically the point is that any operator I have, any operator, you know, this is just an aside. Why are these the same? So any operator I have, any Hermitian operator, okay, that certainly includes the positive semi-definite operators, right? Any Hermitian operator rho, let's say, can always be written as the sum over I of, you know, some coefficients. Let me just call them SI right now, it doesn't really matter, and HI, tensor HJ, if you will. Sorry, I should do it IJ, right? So the point is that, and you can take any operator on this bipartite space, this is just an aside, right? So this, and you can always decompose it in terms of a so-called basis of Hermitian operators for the space. Okay, so these guys are going to be a basis for Hermitian operators. So just like vectors have a basis, right? Hermitian matrices can also have a basis in terms of operators, right? So an example of such a basis, by the way, is that identity plus the 3 Pauli operators are a Hermitian basis for 2x2 Hermitian operators. Okay? So, I don't want to get sidetracked too much here. The point here is that the way you would typically apply the second definition, and the reason why I like it slightly less is because first, if you have an arbitrary density operator, you would need to expand it in this tensor product form, which you can always do, and then apply this one, okay? Whereas, the original formulation just gives you a clean way of doing it in one shot. Okay, now, we have a new toy. Let's play with our toy, okay? Partial trace. Let's apply it to a bunch of states, and of course, ultimately, we'll get to applying it to the Bell state, which is what we set out to do. So, let's play with the partial trace. All right, so the first thing you do is just try it on a bunch of examples and get comfortable with it, right? So, let's try it on example 1. Okay, well, I guess example 1 is literally, the equivalence between these two, or at least shows how this first definition gives you the second one. So let's go through that now, okay? Let's see why this is true, okay? So example 1 is on product states. Okay, and so remember these were states of the form psi1 tensor psi2, and the density operator for this is going to be, well, if you want to be very formal for the first time, let's do it properly. Psi2, like this, right? And that's just equal to psi1, density. So that's a density operator, and then tensor on the second subsystem psi2, psi2. Okay, so this is my density operator rho. So that's my rho. Okay, now I want to do a partial trace. Let's suppose we want to throw out subsystem B again. And let's see what happens, right? So partial trace of B of rho, what is that equal to? So I'm just going to go off my definition before, right, which is the following, which is the sum over I equals to 1 up to, well, okay, I'm not being slightly lazy here. I'm not writing the dimensions down, but it's just plugging in the definition, so let's not belabor the point. Okay, so just like before, I applied the identity onto B, right? And the state I have in my possession, of course, is psi1 on A, tensor psi2 on B, identity tensor I on B. Okay, so that's just the definition of the partial trace. Definition of partial trace. Okay, and now we'll just move the brackets in, right? So this is the sum over I. By the properties of the tensor product, right? These three guys will, everything on A will get paired together, right? And everything on B will get paired together. So it plays very nicely. So this is just going to be, on system A, I have nothing. I have identity times psi1 times identity. So literally nothing happens. On A, okay. Tensor. Here, though, I get I, and then psi2 on B. Okay, that's what I get. And so a few things now, right? So first of all, this thing here, right, the first term here, it doesn't depend on the index I, right? I was only in this broad term, and now that's in here. So I can factor the first term out. So I get psi1 on A, right? And here I get the sum over I. And here I have what? I have the bra of I times inner product ket psi2. And I have the same thing here, but the complex conjugate of that, right? So remember that if I have CC star, that's equal to the absolute value of C squared. So let me take a shortcut here and use this formula, which we've seen a few times now, which is that I could rewrite what's in here like this. Well, actually, do I want to do that? Because I want to get to, I mean, I guess it doesn't really matter. Yeah, okay, it's a bit easier if we don't do it that way. Okay, it'll actually be easier in the long run if we don't skip that step. So what is that? Let me undo that step, right? By which I mean I'm going to write explicitly I psi2 I. Okay, and why am I doing it this way? Yeah, so why did I want to do that? Well, because this is just the definition of the trace, right? This is the trace of the operator psi2. Okay, so this is just the scalar trace of psi2. That's just the definition of the trace. Okay, and psi2 is a unit vector, so this trace here is just equal to 1. It's a rank 1 projector onto a pure state. Okay, and so this just equals to psi1. Okay, so this says that if I start with this density operator here, which is the tensor product of psi1 and psi2, and I toss out the second subsystem, I'm left with just what's left on the first subsystem, psi1. Okay, and that's exactly what this equivalent formulation told you, right? That if I had something in tensor product like this, it's the same thing as keeping what's on the first register and just taking a trace of what's on the second register. And that's exactly what we did. Okay. Okay, so that's the first example I wanted to do. Let's do the second example. So these are product states, and now we can generalize product states. So product states are like the most basic kind of classical looking state because there's no entanglement. But we can actually generalize product states now from the pure state setting here, this is a vector, right, to the mixed state setting, where now what I do is I flip a coin and with some probability I prepare some product state. Okay, and then you get the class of so-called separable states. Okay. Okay, so so recall that a state in let's just imagine the dimensions line up is unentangled, or is product if and only if psi equals to let's say psi 1 tensor psi 2 for some. Okay, so that's the definition we had. And now you could take mixtures over these guys, over these product states, right? So by the way, so the fancy term for mixtures is convex combination. Sorry, my whiteboard here is being slightly slow. Seems like my computer's doing something in the background. Okay, so you can take a convex combination of these states, or just a mixture, if you will. And what you'll get is that, if we generalize to mixed states, then you get the so-called separable operators. Okay, and these are also important. So we say in particular, a bipartite density operator, rho, which is a linear operator, let's just say the dimensions match, is separable if we can write rho is equal to the sum over I. So it's a probability distribution, just like the slot experiment where you flip a coin. And with some probability, you prepare some product state. Okay, so just like before, these guys form a probability distribution. And now these guys, let me be very, very clear, they need not be orthonormal. Okay, so before, when we talked about things like a density operator and we took the spectral decomposition, indeed we got a distribution here, but the terms in the sum didn't need to be, first they didn't need to be tensor products, and also they didn't need to be, they had to be orthonormal, right? But now they can be, now they're forced to be tensor product, and psi 1 versus psi 2, they don't need to be orthonormal. They can in fact even be the same state. Okay. Okay. All right, so how do we compute the partial trace of this? Well, here, I want you to put on your thinking caps, i.e. use your brains, right? And not redo the entire calculation from scratch. But, look at this thing here, right? We already know how to take the partial trace for a product state, like a tensor product of two operators, right? So note down here, I have a sum over these guys. And the partial trace, remember, is a linear map, right? So that means that as soon as you know how to apply it to one term, then you certainly know how to apply it to a sum of terms, right? And let's do exactly that. Instead of doing the entire calculation from scratch, we can just do it in one shot now, right? So we can say that the trace out of B of rho, what is that? It's a linear map, right? So it's the sum over I of pi and the partial trace of each of the terms in the separable mixture. Okay? And we know from the previous example that what is the partial trace of this thing? Well, it's just the first state remains untouched. And then we take the trace of the second part. And this thing just equals to 1. Okay, so it disappears. Okay, so you'll note that, in contrast to the case of the pure product state from the previous example, lagging a bit here. There it is. In contrast to this case, where when we took the partial trace, you just got a rank 1 projector left as a pure state on the left side. Here, the state on the first party is now a mixture itself. It's itself a proper density operator. Okay, so you have more than one term in the sum. Good. So that's how you take the partial trace over separable operators. Okay, so let me just make a side note. Okay, so if you want to figure out whether or not So checking whether a rho AB is product, i.e. rho A, rho equals to rho A tensor rho B, right? This is easy in the sense that it's in P. It's essentially in polynomial time. So we can always do this, right? So for example, we can compute that Schmidt decomposition, which I didn't quite tell you how, right? But you can do it, believe me. Okay? But if you want to check the analogous thing, rho AB is separable. Okay, and you know, the shortest way to write that is that I could write rho equals to the sum over I pi and then times some other, sorry, let me not do it. Let me just do it consistent with how I did it originally. Again, we're lagging. Something funny is going on. Good. Psi I, tensor phi I. So if you want to know if such a decomposition exists for your state, that's much harder. Okay, it's in fact, we believe it's intractable. Okay, so here we already start to see that, you know, these problems involving quantum states, you know, just determining characteristics of them can actually be really quite hard. Okay, so generally speaking, when people talk about checking if a state is entangled, you know, the input is going to be a density operator on, say, two parties, and your goal is to tell me whether or not the state is separable or not, right? And that in general is an NP hard task, so it's much, much harder. Okay, good. So now we can get to kind of the prize of this lecture, which was example 3, pure entangled states, such as the Bell state. Okay, so again, the Bell state is highly entangled, and so it's not clear a priori what should be the reduced state for the local systems, right? So now we can compute it, right? And how do we do it? Let's do the same thing we've been doing, which is, now that we've practiced on kind of easier examples, we take the density operator projecting onto phi plus, right there it is, and you trace out the second subsystem. Okay, and so now this is just a bit of an annoying calculation, but it's not a problem, right? So first, in this ket bra, you know, I have a copy of 1 over root 2 coming out from each from the ket and the bra, so 1 over root 2 squared will be half. So I'll just take out that half right now and forget about that moving forward. And what will I have? I'll have, remember the trace is linear, right? So I'm going to have the trace out of B of 0, 0. There'll be 4 terms in this. If you expand this ket bra, there'll be 4 terms if you expand ket bra of that. So trace out of 0, 0, 1, 1, plus the trace out of B of 1, 1, 0, 0. Okay. So this is what we get. So just use the fact that partial trace is linear. Okay. Okay, and now this is easy, right? Because what do I have here? Now I have the partial trace of product states, right? So this is really 0 tensor 0. Okay. So so let me be clear, right? I'll write it out fully because it's the first time we're doing it. So what we're doing here is we're doing the trace out of B of what? Of 0, 0, tensor 0, 0. And the last one is a similar. 1, 1, tensor 1, 1. Okay. What's less obvious is, you know, this guy, right? Because this isn't a projector, right? This is some funny non-positive operator, right? It's not even diagonalizable, right? And so, but you can still, the Kronecker product still works just fine, the tensor product, okay? Sorry, so yeah, well, tensor product still works fine, and really what it is it's the same thing, right? You just, if you expand this back out, you'll see that you'll get exactly this term, okay? Here it's 1, 0, tensor 1, 0. Okay, that's it. And now we could just compute the partial trace, right? The partial trace of a product state, what did we say? Well, we said that that's the same thing as just basically computing the proper trace on the second subsystem. So what does that mean? Well, that means that the 0, 0 on the first subsystem comes out, and the trace of basically B, sorry, I don't need the B anymore, I suppose. Okay, it's lagging again. Okay. There it goes. Okay, good. So anyway, let's say the trace of 0, 0. Okay, that's just going to be 1, right? So I'm not going to keep writing, well, maybe I'll just do it because it's a bit easier. Sorry, this is 0, 1 now, times the trace of 0, 1 on the right, plus 1, 0, times the trace of cat bra 1, 0, plus 1, 1, times the trace of 1, 1. Whew. Okay, and now we can just simplify this, right? So here we have a half. This term here is just 1 because inner product of 0 with itself is 1. In this term here, you get an inner product of 0 and 1, right, which is 0, right? And same thing for this third term. And as for the last term is just going to be the inner product of 1 with itself, which is also just going to be 1, so you'll get this. Okay, and what is this thing? Well, this thing is nothing other than the identity over 2, right? So, in other words, in retrospect, it's almost like the only possible answer, right, to this idea that if a Bell state is really so tightly bound together that its constituent subsystems make no sense on their own, then the only possible density matrix that describes, say, the state of particle B should be the state of maximal ignorance. We know absolutely nothing about it, which is identity over 2. Okay, so that's how it formally comes about, a description of subsystem B. And if you do the same thing, of course, if you instead trace out, here we describe subsystem A. If you instead want to describe subsystem B, it would be completely analogous. You'd also get identity over 2. Okay, so that's the next exercise in the notes. Okay, so amazing, right? I mean, so in the quantum world, you could have an object about, if you have the two of them together, like the example of the two birds, right? You have the two birds together, quantumly, you know exactly what the birds are doing, but if you just look at one bird alone, it just looks like completely random noise. You have no idea what that first bird is doing. Okay, amazing. Okay, so now one thing I didn't entirely tell you, right? I kept kind of bypassing this, which is, how do you actually compute the Schmidt decomposition? And we still won't do that, but how do we use the fact that the Schmidt rank is greater than 1 if and only if the state is entangled, right? How can I use that to determine if a state is entangled or not? And we can do that now using the partial trace without explicitly computing the Schmidt decomposition. And this is the last thing we'll do in this lecture. Using partial trace to detect entanglement. Okay. Okay, and so here we're going to, I'm not going to do it explicitly, right? The exercise here is going to be that prove that the Schmidt rank of psi, right, which is a bipartite state. So remember the Schmidt decomposition said we could write psi as a sum over I of some coefficients, say alpha I. Well, I don't want to use alpha I because then those things are typically they're complex for us, right? So I don't remember. Okay, let's use SI, right? I don't remember what notation I had used at the beginning of the lecture. Remember we wrote it this way so that these guys are orthonormal bases. and these guys SI were non-negative Schmidt coefficients. Okay, and we said that your state is entangled if and only if the number of non-zero SI was strictly more than 1. So now prove to me that the Schmidt rank of the state psi I equals, right, equals the rank of the reduced state. So meaning the trace out of B of psi psi. So if you throw out either of the subsystems, it doesn't really matter, it turns out. Show me that that equals to a Schmidt rank of psi. Okay. Okay, so once you believe this, okay, like I said, I'll leave this to an exercise. Once you believe this, then if you want to check if a pure state is entangled, there is a way you can do it, right? In, say, Mathematica or whatever your favorite package, right? Which is that, so given psi as input, so compute row A, and typically row A, when we write this, that just means a reduced subsystem on system A. So compute that, and 2, check the rank of row A, right? So if the rank is strictly larger than 1, row A is entangled. Sorry, psi is entangled. And if the rank equals to 1, psi is not entangled. Okay, so, and that, I hope you can believe now, is certainly something we can do in polynomial time, right? At least, with respect to the dimension of this operator, because a partial trace is just this very simple summing and inner producting, which certainly takes time, a polynomial in the dimension. And then computing rank, you just take my word for it that that is also something you can do in time polynomial in the dimension, okay, for all intents and purposes. Okay, so again, please be very careful. I'm claiming you can check if a state is entangled in polynomial time. Note, this only works for pure states. Where did the rest of my thing go? Note, only works for pure states. Okay, so in particular, this trick doesn't work. So here's a cute little challenge. Find a density operator. Rho, which equals to it's a linear operator on 2 spaces. Let's say CD tends to CD. If you want, you can think about 2 qubits. That's fine too. Such that violates this criterion. All right, so that so I want rho to be separable, clearly separable. So you can write down the separable decomposition. So number 1, rho is separable, but it violates this criterion, which means that if you look at the rank of the trace out of B, let's say of rho, that is also larger than 1. Okay, and what is the hint? The hint, as I kind of learned the hard way as I went through undergraduate studies, right, is that the answer is usually in something you've already seen in the lecture, right, or it's some variant on that, right? So look to the past. Okay, so the answer is in the lecture. Good. So so that's basically all I really wanted to say for this lecture. So in the beginning, we started talking about the null cloning theorem, right? Which was kind of like an offshoot of this lecture, but it still is a very important theorem that everyone, I think, should know in the field. And then we start talking about entanglement, this idea that 2 parties can be so strongly bound that the individual parties themselves, kind of their description makes no sense. Like we have no knowledge of it, right? And to formally model all of this, we use the density operator framework, right, which now talks about matrices. And using all of this, we put it together with this partial trace, which allows us to, model what it means to throw out part of a subsystem, okay, or just ignore it, basically. Together, we were able to show that, if I take the Bell state, if I trace out half of it and I just look at, say, the first subsystem, then it indeed looks like noise. Okay, it looks like I have no idea what's going on there. Identity over 2 in this case. So maximally mixed state. So the very, very last thing in the notes, which I won't say really anything about, is you could, but let me just, it should be said, which is that the postulates of quantum mechanics, right? Postulates of quantum mechanics for mixed states, right? So the way we introduced the postulates was all in terms of pure states, right? Because already at that point, I think it's quite a lot to take on at once. So typically they get introduced in the pure state formalism. They pretty much all extend in a very straightforward fashion to mixed states. And this is in particular why when we talked about measurements, I was really already writing things in the mixed state formalism, right? Just to ease that transition. So I won't really say anything here. In the future, if we ever need to say, oh, this is how the postulate extends to mixed states, well, we'll do it explicitly case by case. But it goes exactly how you would expect. Let me just, so it goes straightforwardly, or I shouldn't say it goes, I really want to say extends straightforwardly from the pure state case using facts such as, okay, so a few facts you need are that, number one, if rho and sigma are both positive semi-definite, then, well, remember we use the tensor product to stitch things together. And so we also need to argue that the tensor product of density operator should still be a density operator. And so you can prove that, this is also going to be non-negative. Okay, and how, by the way, again, challenge, how do you prove this? How to prove. And again, here, you should really think carefully about which characterization of PSD-ness would be the easiest way to prove this. Okay? And the other thing, for example, is that we need the trace of the tensor product to still be 1, so that you maintain the fact that when you take a tensor product of density operators, you still have a density operator. And you can verify, sorry, you don't need a tensor product here, because they're scalars. That really just equals the product of the traces. Okay, so if rho and sigma in particular were a trace 1, then the product is still trace 1. Okay, so that's really all I want to say for this lecture. Okay, so now we have density matrices under our belt as well, and so now we have a fairly good grasp of how to describe quantum states and how to start working with them. Okay, and maybe I'll just close the lecture there. So I hope you guys have a good week. Again, the next assignment should be out soon. In the meantime, feel free to send any questions my way, or as always, preferably to the news group first, because it seems like there's some really nice discussions happening there. Okay, good. Have a good week. Stay healthy.